All right, hello. Uh, Welcome back. Apologies, this lecture is super late, but that'll be the end of it. I'm back home, and hopefully we'll be back on track starting this week. Um, Today and this lecture, we're going to start digging into how a computer represents information such as integers and floating point numbers, which you may already be relatively familiar with at this point. So kind of let's dive in. So with regards to numbering systems, we're used to the base 10 numbering system, right? We have digits 0 through 9. Once you get to the end of that list, 0, 1, 2, 3, 4, 9, and then you put a 1, and then you start over again. So each position represents an order of magnitude, by an order of magnitude meaning 10 to the power of that position. So if you're at the 0 digit position, that's 10 to the power of 0, which is 1, right? If you're 1 over, then that's 10 to the power of 1, which is 10. And so if you take each digit, what you would do is you would multiply that number by the respective 10 to the power of that number, and then add everything together. For example, in the case shown here in the slide, 1, 2, 3, 4, or 1,234, the 1 is multiplied by 10 to the 3, plus 2 times 10 to the power of 2, plus 3 to the power of times 10 to the power of 1, plus 4 times 10 to the power of 10, which is 1. You can see how that breaks down, and then the summation of those ultimately give us 1,234. But this is possible with alternative numbering systems. For example, you may already be familiar with the base 2 or the binary numbering system, where each digit can have one of two values, 0 and 1. And then each position of the digits, as we go incrementally up, we're basically adding 2 to the power of that position in the digit. So for example, in the case of 10110, right, a 5-bit binary, we multiply the different pieces together, we get 22. But to go through it, right, the most significant bit, which is important to note that the leftmost bit in this case is the most significant bit, is 1 to the power of 1 times 2 to the power of 4, which is 16, right? And then the next one is 0 times 2 to the power of 3, but that's 0, because 0 times anything is 0. 1 times 2 to the power of 2 is 4, so now 16 plus 4, so we're already up to 20, right? The next number over is 1 times 2 to the power of 1, which is 2. So right now we've had 16 plus 4 plus 2, which is 22, and the final digit is 0, which is 0. So the addition of all of those powers of 2 results in the final number of 22. So this is just like the base 10 system, just using 2 as the base, which if you're already been programming for some time, you might appreciate the reason why we care so much about the base 2 numbering system. Most computers are built off of this logic. There are other numbering systems, so for example base 16, so if you've used hex before, this goes 0 through 9, but then we're out of numerical digits, and so we use the letters A through F, and this gives us 16 total values. For example, A217, and I'm not going to go through the whole breakdown again, results in the equivalent value of 41,495. Hex numbering is particularly helpful in that one value, right, F, or 16, is equivalent to a nibble, which is 4 bits. So if you're familiar with a byte, which is 8 bits, a nibble is 4 bits. So a 8-bit number can be represented by 2 hex values, which when you're representing these large numbers, sometimes, hex is very, very helpful. Whereas if you were to break it into the binary representation and you have to, say, write 32 bits of information of 0, 1, 1, 0, 32 of those, especially in code, that could be really annoying. And then to represent that number as a numerical value, sometimes these values have kind of special significance and things, is also kind of not as helpful as using the hex, both because it's more condensed, it kind of helps represent the structure of the underlying binary data in a way that decimals cannot. Like as I mentioned, each hex value is a nibble. So if you're looking at, say, a 32-bit value, you can split up the pieces into sort of these chunks of, if you've ever used like hex values for setting a color in HTML or something like that, right? I'm sure you've seen the, FF, AA, FF, which is a much easier way to read than some conglomerate, like amalgamated value of that translates into. But you know that RGBA, FF is red, AA is blue, and so on. So hex comes in handy very often because of its alignment with the modern computer architectures that are being used, such as 8-bit, 16-bit, 32-bit, 64-bit, 128-bit, and so on. Whereas higher hex, there are higher that you can do whatever you want, right? But at a certain point, it's kind of hard to keep track. So if you were to use the entire alphabet and get to base like 32, could you do that? Yeah, you could. It's not so easy to kind of understand. So yeah, hex is particularly valuable and helpful in programming. So here's a little bit of a kind of representation. As I mentioned, hex is effectively like a nibble, right? 4 bits, and you can kind of see how those bits translate from decimal to binary to hexadecimal. And for those of you who are interested, almost every calculator, be it Windows or Mac, provides a sort of programmer mode. So if you're ever interested in sort of the conversions between these, you can use the programmer mode in the calculator in Windows. Just use Alt-3. I don't know how to do it on Mac to automatically change it, but you can change it from normal to scientific to programmer, and then you can effectively take a decimal number and convert it into binary or convert it into hexadecimal, and vice versa, which is actually super, super helpful. Many IDEs provide this capability as well, but often you just want to know what a value is. But like Visual Studio, for example, will let you change the representation in the debugger from decimal to binary to hexadecimal to whatever you want, and which is also very, very helpful when developing. So when you're using C, and in most programming languages at this point, this has become pretty standard. If you want to represent a hexadecimal number, what you would do is you would use the prefix 0x, lowercase x. So it's a 0, x, and then the value. And that will tell the compiler or your respective IDE or whatever you're using to convert that in value to effectively a hexadecimal number. Some programming languages will also allow you to use 0 lowercase b for binary, and then you can put in a binary value. Some languages just use b and other prefixes, so just, whatever language you're using. For example, Rust just uses B. It doesn't do anything special. I think it just uses X as well. You don't need to have 0. So some languages are getting more and more, shorter, just, saving you a keystroke because that's critical or whatever. But yeah, this is how you represent a hex value, at least in C and in C++. So to convert from a decimal to a hex, this is sort of the way you would do it. Essentially, well, I'll be honest, the way that I do it is I take from hex to decimal, right? What I'll do is I'll simply run through each value, right? And this is sort of an algorithm to do that, and you go bit by bit, digit by digit, calculate that to the base of 16 and add it to your summation and go through it, and now you've got the binary, the representation of that. To convert it from the other way around, if you want to take a binary value, a decimal value, and convert it into hexadecimal, what you're doing is you're essentially dividing it by 16 and then modding it by 16 now and removing that value, essentially. So you take the remainder and then move it over. Let me kind of walk through this. For example, if we wanted to convert this value in the slide, 29,134, into hexadecimal. So we would start and we would divide 29,134 by 16, and that would give us 1,820. The mod of that same value is 14, so that gives us our first value, right, E. And now we repeat the process on 1,820. We divide, now we know that that's the next value we're going to be modding, and then we mod the existing value 1,820, and we get the next value, 12, which is C. And then we do the same thing for 113 and 7. So we are now getting EC17, right? And 7 being the most significant value, we get 71CE. Now if we wanted to convert it backwards, right, we would take E, which is 14, to the power of 16, times 16 to the power of 0, which would just be 14, and we'd add that to C, which is 12, times 16 to the power of 1, and so on and so forth until we get back the total value of 29,134. I do recommend you going through this process yourself. I mean, the algorithm is relatively intuitive, but it's good to do this a couple of times just so you kind of get the process. So if this question happens to be on an assignment or a test, you know how to approach it. That a lot of it is actually pretty straightforward logic, right? If you know what the underlying digit system is based on, right, the conversion from one to the other should be pretty straightforward. To do a similar thing for binary, and again, like if you're doing this, I also recommend pulling up the calculator in programmer mode and sort of messing around with it and sort of making sure that your logic is correct. But to convert 44 into binary, it's exactly the same process. I personally actually like to mod it first. So 44 mod 2 is going to be 0 because it's an even number. And then we divide 44 by 2, which is going to give us 11, right? Now, 22. 22 mod 2 is going to be 0, again, because it's an even number. So now we have 0, 0. And then we have a 11 as the new sort of underlying thing because we've taken 22 and divided it by 2. And now we have 11 mod 2 is going to be 1. And 11 divided by 2 is effectively going to be 5. And keep in mind, we are working in integers, right? We're flooring everything. Because it's as if we're taking that remainder, the mod, and removing it from the number and then dividing it. So it's actually something that you could do here if you'd like, where first you mod 11, you get 1, then you subtract 1 from 11, then you get 10, and then you divide 10 by 2. But it doesn't matter, flooring it is going to give you the same result. And then we have 5, we do the same thing, and eventually we get the final number, which is 101100. And if we really want to play with this, right, we only have 3 values here, which are 1, right? So we can see that we have 1 times 2 to the power of what looks like 5, which 2 to the power of 5 is 32, right? And then we've got 1 to the power of what looks like 0, 1, 2, 3, so that's 8. And so 32 plus 8 is going to be 40. And then the last one that we have that's in this number is 1 to the power of 2 to the power of 2, right? 0, 1, 2, and that's going to be 4. And so in total we have 32 plus 8 plus 4, 44. And so you can kind of walk this process kind of in either way. So the range of our values, and this is important, given that we can represent sort of any value with any numbering system, but we need to have a sufficient space and range to do so. Unlike a piece of paper, when you can write down any number at any length, when you're dealing with a computer, you're passing values through a bus. This is hardware, right? And so this is something that's kind of, when we're programming, we'd like to pretend like there's no limitations, but that's not true, right? Some numbers cannot be stored physically or passed through the CPU just in a very easy way. And so when you think about writing programs, you do have to consider the underlying size of your value. So if you've written C or C++, you probably know this in terms of bytes, or chars, which are 1 byte, and shorts, which are 2 bytes, and integers, which are often 32 bytes, depending on the architecture you're on, and so on. And so the size of the maximum value of a given value is going to be limited to the number of bits that it has. So say you have 4 bits, right? The maximum number of values there is 2 to the 4, or the number of bytes, 2 to the power of 4, or 16 values. For 8, it's 2 to the power of 8, which is 256. So the general formula for this is 2 to the power of the width of the number of bits that you have. For unsigned values, right, the number of values this can represent is 2 to the power of the width of the number of bits minus 1. And the reason is because 0 is one of the values, and so you have to deal with that. When you're signed, that's a little bit different. We'll talk a little bit about that later. But for example, in the context of 2 to the power of 8, we have 256 values, but we can only represent 0 through 255, because 0 is also a value. So if we don't want to support 0, we can go up to 256, but there will never be a 0 value. I'm noticing on the slide here that it's the values is 2 to the w minus 1. The minus 1 is actually 2 to the w minus 1, not part of the exponent, and I'll fix that in the slides in a moment. So sorry for the confusion there. So when you think about addressable ranges in the context of computer architectures, you've heard of 32-bit systems. Most computers today are 64-bit, but some are still floating around which are 32-bit, and you'll even run across 8-bit and 16-bit systems when you're working in embedded and kind of alternative computer systems, and often. So in the case of a 32-bit system, right, we have what's called an addressable range of 4 gigabytes, or 2 to the power of 32 potential values. And the reason we call this an addressable range is because often, we have a system with memory, and we need to be able to point into memory and say, okay, hey, I want memory here and I want memory there. And when your architecture, your system is designed with a 32-bit bus, yes, you can write software that will allow you to create kind of a dynamic range and sort of pretend, but your performance goes down significantly, which we'll talk about more in the rest of this course. So often, operating systems limit their sort of addressable ranges to the architecture of the underlying computer, which in say a 32-bit system is going to be 4 gigabytes. So one of the big reasons that people went from 32-bit systems to 64-bit systems is because of that limit, of that sort of memory limit. You could use more than 4 gigabytes of RAM on your computer in a 32-bit system, but it was significantly slower than using the 4 gigabytes of your system because of all the additional logic that had to be placed in programs and in operating systems, and it just was something that it was actually easier to just move to a different hardware than to write software in a funky way for the rest of time. The move to 64 bits is quite a jump. So once you get to, when you add 1 bit, you are multiplying your range by 2, right? So just if we had 33 bits, that would have been 8 gigabytes, and 34 bits would have been 16 gigabytes, right? And then quickly you get up to large numbers. And so 2 to the power 64 is 11 exabytes. There's going to be some time before we are able to sort of catch up with that memory limitation. So depends on the computer system that you're on. Some of these values are not always going to be true. However, this is pretty generally true in most systems. And this kind of represents the data width. So you might already be pretty familiar with this stuff, especially if you took the prerequisite for this class, which is 309, and you had to write stuff in C++. So a car is usually 1 byte on all systems. It kind of represents like an ASCII car. which actually is kind of like problematic now because most things are Unicode and require at least 2 bytes of information to represent, but never mind. Cars are 1 byte. A short on most systems is 2 bytes. An integer on most systems is 4 bytes, which is 32 bits. Although beware, because sometimes it'll be 64 bits. So you do need to kind of pay attention there. A long and this is one of the places which you kind of get caught up. A long in a 32-bit system is 4 bytes, whereas in 64-bit systems and in x86 64, or also referred to as AMD 64 often, or is again 8 bytes. A pointer, and this is really kind of referring to the thing I was saying about before about the addressable range of memory. A pointer is always going to be the maximum size of the sort of of the bus width on a given system. So in the case of 32-bit systems, that's going to be 4 bytes. On 64-bit systems, that's going to be 8 bytes. And you actually really have to be careful with the pointers because that's a pointer to any type. It doesn't matter if it's a pointer to a car, you're still dealing with an 8-byte value on a 64-bit system and a 4-byte value on a 32-bit system. This is a constant source of bugs between 32 and 64-bit systems. And it also is kind of a funny thing because if your pointer is bigger than your type, then what's the point, right? So like, what's the point of having a pointer to a short on any system, right? Or what's the point of having a pointer to an int on a 64-bit system? You have twice the memory requirement. Now there are arguments, but for the most part, you'll find that they're going to be pretty bad. Floats are always 32 bits. Usually, you can or sometimes you can have doubles, and a double is kind of like a float, but it's twice. So like a floating point number, when defined with a float, is going to be 32 bits, or what's called 32-bit precision, which we'll get into in the rest of this lecture. Whereas a double is going to be 64-bit precision, and then a long double, it's very dependent on your system. So it can either be 10 bytes, or 16 bytes. So it depends. Long doubles are pretty rare, usually in scientific computing and stuff like that. In games, you'll actually find that more often than not, a 32-bit floating point is used versus even a double, because there are not as many good reasons to use double point precision for floating point numbers, unless you have to have a really good reason. And we'll talk a little bit about that in this lecture as well. So endianness is, we talked a little bit about least significant and most significant. Now, this is kind of a bit of a sticky thing, and I'll admit that I still get this wrong all the time, and I have to look it up most of the time, because on the one hand, you've got the most significant and least significant bytes, and so what endianness means is which byte is most significant, and by most significant we mean bigger, ultimately. So the most significant byte is going to be the largest portion of the number, right? So the 1 on the left side of that byte is going to be to the maximum value. So if you have a 32-bit number, that 1 will be 2 to the power of 31, well, unless you're signed, but anyways, right? In the least significant byte is going to be the last byte. So what does endianness mean? Endianness means which, in what order in memory is your values stored? So in big endian, the most significant byte essentially goes first. Which first, how do you define first, right? Is it, if you have memory and it starts at 0, right, and it goes up to 2 to the power 32, right? These are locations of memory, and these are bits essentially, right? The idea is that in big endian, the most significant byte goes at 0. So it's kind of like backwards, and maybe I'm not describing this particularly well, but it's kind of unintuitive. Big endian actually is not used as often. The only system that I know of that uses big endian actively is PowerPC, which has kind of gotten phased out in lieu of x86 and systems like that. Whereas in little endian, it kind of behaves more intuitively, where the least significant byte goes first in memory. So you kind of have. Let me pause this because I want to make sure I get this right and don't misrepresent this. I'm gonna make sure that this is the case. Yes, okay, I'm correct. I just want to make sure that I'm not leading you guys astray with this, because it's still something that I trip up over. Essentially, to really kind of be specific about it, right? As memory goes up in value, then the first is on top, and so little endian, as you go up in the memory space, the the values become more significant. So this is kind of like normal, because while we think as memory is incremental, the values are actually getting bigger and going down or going up. So first is kind of upside down, and so little endian is the way that you would imagine it, because memory starts at 0 and goes up, right? And then values. So basically, if you had an integer of 4 bytes, and it was stored at location 0, right? The least significant byte of that integer will be stored in 0. So say we have an integer of 0x55AA1122. 22 would be stored at location 0. 11 would be stored at location 1. 55 was it? Location 3, 2, and AA would be location 3. So that's little endian. Whereas with big endian, it would be the opposite, where at 0 you would have AA, and then you'd have 55, and then 22, and then 11. It's kind of backwards. But again, x86 tends to be the de facto, and sometimes you'll see architectures that can switch between the two of them. There are benefits to switching endianness specifically with regards to how you transfer data. So say I have two computers communicating with one another, and you kind of want to not have to have one computer sort of switch things around. And so it takes data out of memory in a particular order, which is then passed across, say, a serial bus in a particular order, which then received by another computer in a particular order, and then put back into memory in a particular order. And if you know the endianness on both sides, you know which protocol and what way to pull data out of memory and to pass it across the bus, such that you don't lose any performance. So you're probably not going to come across too much of that unless you're doing embedded level protocol programming and stuff like that. But it is important to kind of know about the differences in endianness. And it's a bit of a sticky subject, and something that even I struggle with, as I just did, pretty much every time I come across it. So yeah, let's move on. So let's kind of talk a little bit about this, and I didn't realize this slide was here. So in the case of big endian, you can see that the value 1, 2, 3, 4, 5, 6, 7, 8, you can see the most significant value here in the memory address in 0 is 12, and it goes up to 78, and in little endian it's the other way around. So funny enough, for us, for human beings, little endian is much more intuitive, because if you sort of think about memory as starting as going down, actually we intuitively you don't think about it going up in the way that it's architected. So this kind of demonstrates that. Yes, so we already talked a little bit about that. Intel is little endian, Sun PowerPC is big endian, and it's important to know about this with regards to serialization, which is the way that you would take data from one memory and pass it through a network or some kind of bus to the other side, which is going to be received by another computer. So strings are a form of data, right, that we store pretty often. We talked about cars taking up 1 byte, and let's hold on to that for this example. But as I mentioned, Unicode, which is pretty much used everywhere now, is 16 bits. So when you're programming, I'm sure you've come across wide string versus not wide strings. And when you say wide strings, it just means Unicode or 16-bit characters versus 8-bit. But in the case of the string A, B, C, D, E on, on a system, you can kind of see that this is sort of backwards than from what we're talking about little endian. And then this is not because we're not on a little endian system. It's because our values are 8-bit or 1 byte in size. So at memory address 0, we have A, memory address 1, we have B, and so on. And so it goes up. Now, this is just a good example. If we were to have say a Unicode string, right? A would take up both location 1 and 0, but the ordering of the data, the most significant byte, would be in location 1. And then, so it's kind of weird if you have these values which are going up in memory location, but their direction is in the opposite, kind of against the stream. I'm not going to go too deeply into that, but just kind of picture, if you, for your own benefit, try to, on a piece of paper, take a memory, like write out your memory from 0 to say 16, and then write out a integer array, or a short array, either way, and kind of understand how, while the last value is going to be down at the bottom of memory, but the direction, the most significant byte of that is going to be at the tip of memory, and it's kind of going in a backwards direction, where you're going the first value, the second value, the third value, right? But the most significant byte of the third value, the most significant byte of the second value, and so on. So it's a nice, just kind of to visualize it. It's a good idea. Let's talk a little bit about Boolean algebra. So Boolean algebra is the algebra of basically Boolean values, which is another way to say binary representation of numbers. Ultimately, we have two values which are 1 bit long, so A and B, and both of these values only have 1 bit, so they can represent either 0 or 1. And so Boolean algebra allows us to operate logically on these values. The reason it's called an algebra is because it's a type of math that we apply to Boolean values, but essentially this is a kind of logic, because 0 and 1, there's no continuous values between those two positions, and so it's a kind of logic where we can say this and this, or this or this, and we'll talk a little bit about some of the examples, some of the operations we can do. So for example, and, right, when we say A and B, then that means that both A and B must be 1 for the result of that to be 1. If either A or B are not 1, then the value is 0. You may have heard about what's called a truth table, and we haven't put a truth table here, but each one of these logical operations has a truth table. In the case of A and B, the only position of the truth table where the output of that is 1 is when both A and B are equal to 1. And for anything else, it's 0. There is another operation called OR. So in the operation of OR, it's kind of the inverse of AND in a way. Not inverse, that's not really fair, but it's kind of the opposite in that A and B must be 0 for OR to equal 0. So for any other value, so if A is 1 or B is 1, or they're both 1, the value is 1. So uh, or and are not inverses of each other. That would be nor and NAND, which are just the opposite of those operations, but they're kind of very different. They're kind of opposite. They both are going to be 1, however, if A and B are 1, but in the case of OR, this is pretty logical, right? Like this or that, and if this or that is 1, then it's 1, right? And this and that, you know. XOR, or XOR, is called what's called exclusive OR. So the exclusive OR is not equal to 1 when both A and B are 1. So it's A can be 1 and B is 0, that's going to be 1. B is 1 and A is 0, that's going to be 1. If both of them are 0, the value is 0. If both of them are 1, the value is 0. Exclusive OR is actually not a trivial function to implement. It's not really possible to build it logically as sort of a very simple function, or basically as one linear. Like it's a combination of linear functions. You can't actually have it as just an individual linear function, and in that sense, it's a pretty dynamic function. If you're interested in it, check out if you have the ability to represent an XOR using neural networks or logistic regression or something, because you'll find that it's actually pretty difficult to do. It's pretty cool. It's a cool function. And the NOT is actually only applied to one value. Basically, it takes the input and inverts it. So if you have a 1, you get a 0. If you have a 0, you have a 1. And again, I mentioned already, for and OR, you have kind of the inverses, which is NAND and NOR. So not or NOR is the opposite of OR. So you have, say, A is equal to 1 or B is equal to 1. For OR, that's 1. But for NOR, that's 0. So for NOR, both values have to be equal to 0 to get a 1. And any other value is going to be 0. So there's some really, if you're interested in Boolean logic, there's some really interesting ways to sort of convert and break things down, especially when you get to kind of complicated combinations of these, these functions. Okay. So, in the case of Boolean algebra for integers, say you take this of two values and you apply Boolean logic to them. How do you do this? Well, it's actually pretty simple. The way you would do it is you would take each individual digit and then apply that operation to it at digit to digit. So for example, here we've got 0, 1, 1, 0, 1, 0, 0, 1, and 0, 1, 1, 1, 0, 1, 1, 0. So to get the output of these two operands, we would take 0 and 1. That'd be 0. 1 and 0. That'd be 0. 1 and 0. Again, 0. Right? We keep on getting zeros because none of these match up. The only place these two numbers match up in terms of having ones in the same digit locations are for these two, for the two ones in the front. So you can see there's 1, 1 here, or 0, 1, 1 here, 0, 1, 1 here, and so the value is 0, 1, 1. So in those locations, both integers, both values have ones at that digit location, that binary digit location. And so it's sort of like take the two numbers and sort of smush them on top of each other, and whenever there's a 1 in the same location, there's a 1 in the output. Now the OR is similar, except instead of making sure that there's both of the ones, it's almost like you take the two numbers and squish them on top of each other and save wherever there's a 1. So in this case, right, there's a 1 in the 0 in the first digit, so there's a 1. There's a 0 here, but there's a 1 in the opposite one, so there's a 1. You can see that the sort of mishmash of the two, basically there's only one location in these two numbers where they both have zeros, and that's in the first digit, and so that's the only place in the final result that you get a 0. I recommend trying this out with different numbers just to kind of get a feel for it, but for the most part, it should be pretty straightforward. This is an interesting use case of Boolean numbers. You can actually kind of treat them as what's called as sets, right? Ultimately, if we think about each each binary location representing a number, the number that is the location. So in the case of say 011010001, there are 8 digits or sort of 7 fundamental numbers that represents. So in the case of this number, this represents the set of 0, 3, 5, and 6, because we have ones at 0, 3, 5, and 6 locations. And same here, in the second number we have here, you can see this represents the set of 0, 2, 4, and 6. So if you treat the AND as an intersection of these two sets, you get 0 and 6, because 0 and 6 exist in both sets. If you talk about the union, right now you have every number, all these numbers, 0, 2, 3, 4, 5, 6 represented, and now you can essentially get the different values. You can also do the symmetric difference and the complement of these values, which ultimately gives you the numbers that are missing. And I'm actually not familiar with the symmetric difference personally. Let me pause so I can talk about that. Okay, sorry. So the symmetric difference essentially is the inverse of the intersection. So it represents, if you take the symmetric difference of two sets, it's basically all the numbers of the two sets combined that are not in the intersection, right? So in the case of this, you would take the union and you would remove from it the intersection. So you'll notice 2, 3, 4, and 5 are in the symmetric difference, but not 0 and 6. So it's sort of like imagine like a Venn diagram of the two sets, and then you remove the intersection. The complement is literally what it sounds like, which is sort of the opposite. So in the case of this is actually the complement of the second number, which is 1. So the number here is 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. So the complement would be 1, 0, 1, 0, 1, 0, 1, 0, which is, as you can see. So it's kind of the opposite. The complement is just like the not applied to the number. Sorry for the quick hiccup there. Logical operators are a little bit different in programming in that they're not applying bitwise operations to the values. They're simply dealing with logical operations. And that the difference is, say you have a number 55 and you AND it with another number 77. The result of that, the logical, if you're using both and, not the bitwise, you're using the logical operation AND. So 55 and 77 in C is going to give you true. Huh? What does that mean? It's because both numbers are greater than 0, and so they're treated as a true by the compiler. So basically your true and true is going to be true. So if you take 55 and 0, you're going to get false, because 0 is treated as a false. And this is actually kind of a tricky thing, because some compilers are going to be weird about it, and so it's really important to be really sort of explicit when you're writing this kind of code. And so these are the ways to use the logical operations in C and C++. A double line is an OR, a logical OR, a double ampersand is a logical AND an exclamation point is a not. And actually the not is the most annoying one, because not something, not a number, is going to give you the opposite of its sort of logical representation. So like say not 55 is going to give you false, which is like what, like I really encourage you guys to Google WAT like JavaScript. There's a very funny video about the funky, stupid things that languages do. But that's a good example of one. Like exclamation point 77 is going to give you false. Like it's like, what? That doesn't quite make sense. But it does if you understand that when you do that, it takes that value, converts it into a logical operation, and then knots that operation. So it takes 77, evaluates it logically, which gives you a true, and then has a not operation on that, which gives you a false. So it's important to kind of, pay attention to that. Yeah, and as you can see, you can sort of write some code that makes 0 sense for some things that kind of are useful, but please don't do this. Please don't write code that makes no sense. Please write code that makes sense. Let me talk about shift operations. Shift operations are essentially bitwise operations, meaning that they apply to numbers at the bit level. A left shift means that you're taking a value and you're shifting it left by y bits. What does that mean? What are you shifting? Shifting left, right? Say you have 0, 0, 0, 1, and you shift it left by 1 bit. So now you're going to have 0, 0, 1, 0. So that 1 moved over 1 bit. So what happens to the bits on the left? Well, they die. They just go away. And what happens to the bits on the right? The ones that are not there? Well, you just fill it in with a 0. And then the right shift does exactly the same thing, which will ultimately fill up your number with zeros from the left and kind of move things over into the abyss. Keep in mind, however, with a right shift, it will signed extend your shift on the left. Meaning, if you're a negative number, it's going to do this in the 2's complement format, which if that sign bit's a 1, it's going to copy in 1s. If the sign bit is 0, it's going to copy in 0s. So right shift kind of is a little bit more temperamental. Now, this is useful in many situations, but the place that I find it most useful in is a left shift or a right shift can be treated as a divide by, or a divide or a multiply by 2, right? So if you shift to the left, you've basically increased every single digit's value to the power of 2, right? So if you have 0, 0, 0, 1, which is 1, right? Multiplying it by 2 or shifting it to the left would give you 0, 0, 1, 0. Now, 1 times 2 to the power of 1. If you shift it over again, you get 4. If you shift it over again, you get 8. Sorry, well, 7, right? Because it's, no. Yeah, 8. Yeah, sorry. And so if you have 0, 0, 0, 1, which is now 8, and you left shift it again, well, you get 0. So it's you have to kind of consider the bitwise logic when you do this stuff. Similarly, right shifting is going to divide by 2. So if you're at 8 and you right shift, now you have 4, and so on. And so given that multiplication and division in computers tends to be an expensive operation, whereas bit shifting is not, sometimes it's really, really nice and effective to bit shift instead of multiplying. This also has implications for the use of what's called fixed point numbers, which we'll talk about in a minute, because it essentially represents moving your decimal point by 1, which, if done correctly, can be quite effective. But really, it's just a division. So yeah, shift operations are pretty helpful. Whoa. Same? I guess so. C does not define the type of shift, whether it be a logical or arithmetic. So it just conforms to unsigned and signed. The arithmetic shift will take into consideration the signed bit, as we were talking about. But the logical will just not care and will add zeros. So in C and in C++, there is no use the logical or arithmetic, but things like Java, for example, do have an additional operator, which is 3, whatevers, to give you the logical if you want. But I don't know how often logical is used compared to arithmetic, and the truth is these are relatively niche things. When you're doing bitwise operations, you're being pretty careful already, and so for the most part, you don't have to really deal with that. Um, we don't C does not define shift when the value when you're going less than 0. Uh, so for the most part, when you take a 32-bit shift on a 32-bit value, it results in the same value, which is 0. But um, in short, like when you do a shift that's bigger than your size of your thing, it should result in the same value in most compilers, but like it does. This is where a lot of the bitwise stuff is a little bit nitpicky, and this is also why people don't use it very often, except for very, very controlled cases, or when you're dealing with bit level kind of operations, such as data formatting alignment, and things like that. You do need to be really careful. So when you should not be shifting willy-nilly. If you have a 32-bit value and you're shifting more than 32 bits, like why are you doing this? But if you do, you're going to get, in many cases, undefined behavior, or it's not going to be the same across different compilers. So just be aware of that. Cool. So there are two kinds of integers, and you'll actually find this to be true in other kinds of values as well, like floating points as well. It's basically signed and unsigned. The way that compilers and computers represent negative numbers is by utilizing the most significant bit as effectively a signed bit. And when that bit is 1, then that means that your value is negative and is represented in what's called the 2's complement. We will talk about the 2's complement in just a moment, but to kind of go through the two types, we have got unsigned and signed. In the case of, for example, 4 bits with unsigned, as we talked about, the maximum value is 2 to the w, or the width, which is 4, minus 1. So it's correct in this slide. So you have the values 0 through 15, which can be represented by 2 to the power of 4, by 4 bits. With 8 bits, that's 256 values, but a maximum of 255. 0 to 255 is the range. In the case of a signed integer, right, because your high order bit is used for the representation of the sign of the number, be it negative or positive, the number of bits you have left to represent the actual value is 1 less. And so in this case, the maximum number of values we can represent is sort of 2 to the power of w minus 1 minus 1. So we can basically go to a maximum of, imagine the number, right? So we have 4 binary digits, 0, the maximum would be 0, because that's a maximum positive would be 0, 1, 1, 1, which is 1 plus 2 plus 4, which is 7. And the maximum negative value would be 1, 1, 1, 1, which is 7, the complement 7 minus 1. Negative 7 minus 1, which is 8, negative 8. Which is a little bit weird, and we'll talk about 2's complement in a minute. And then we've got the 8 bits, for example, which 2 to the 8, or 256 values, turns into 2w minus 1 minus 1, which is 120, negative 127 to 126 should be the value there, I believe. So I think this slide is incorrect. Or it should be negative 128 to 127. Yes, that should be the number. So those two numbers should be flipped. But yeah, we'll talk about 2's complement in a minute and how that works. So the the way we would represent, for example, a value that has a positive, as we talked about before, say 0, 1, 1, 0, just like before, we expand it out into the respective sums of all the pieces, and we get 6. So, right, so 1 to the power of 2, 1 times 2 to the power of 1, 1 times plus 1 times 2 to the power of 2, which is 4, so 4 plus 2 is 6, 0, 1, 1, 0. In the case of this next number, we actually have 1, and 1 to the power of 2 to the 3, negative 1. In this case, because this is the 2's complement, is 8. And against 8, we now add the remaining numbers. So in this case, we add to negative 8 4, and we get negative 4. So you can see that the maximum value of a negative number is when it's essentially empty. Because what we would do then, so we would complement it. And actually, in the binary world, the way you would do this, so say you have the value 1, 0, 0, 0, right? Which is, in this case, negative 8, right? The way you would do it is you would take the complement of that, and then you would add 1. So in that case, we would take the complement of 1, 0, 0, 0, which is 0, 1, 1, 1, which is 7, and we would add to it 1, and that would be then multiplied by negative 1, and that would give you the 2's complement, which is negative 8. So in this case, so for the 1, 1, 0, 0, the way at the binary level we do this is we would complement the value. So what we would get is actually 0, 0, 1, 1, which would be 2 plus 1, which is 3. We would add to it 1, which would give us 4, and multiply it by negative 1, which is negative 4. So that's why it's called 2's complement, because you actually take the value and then you complement it in 2. And the reason that we do that is because then when we add these values together, we get kind of a similar outcome. The way that the addition, the adder units work at sort of the computer architecture level give us the same result. So for example, if we wanted to add 0, 1, 1, 0 and 1, 1, 0, 0, we would first complement the 2, and this is I can talk to this more in office hours if anybody's interested. This actually just goes down into the grit of how actual adder circuits work, which might not be that interesting. But to kind of go into sort of the comparison, right? When we're talking about unsigned values, you can see from 0 up until the maximum value, it just goes 0 to 15. And in 2's complement land, we go 0 until 7, at which point we hit negative 8, as we mentioned, and then it goes down from negative 8 to negative 1. So you can kind of see that 1, 1, 1, 1 is negative 1, and then 0, 0, 0, 1 is 1, and they're kind of like almost, they're nearly opposites, where negative 1 is the effective complement of 0. And so this actually is a good place to exemplify this. So imagine if you wanted to add negative 1 to 0, right? You know, not going into the details of how binary addition actually functions, you'd imagine if you take 0 and you add it to 1, it's kind of like you're just sort of ORing them, right? You're just sort of inserting, it should be just equal to negative 1, because any 0 plus anything is that thing, right? And you can kind of see that that's true. When we take 0, 0, 0 and we add it to 1, 1, 1, 1, we get negative 1, because the result is going to be 1, 1, 1, 1. And actually, this is true for sort of any, if you wanted to sort of take an example, and I won't go into too much depth, but say I wanted to add negative 1 to 5, or actually in the case of maybe it's easier to look at negative 1 plus 1. So in this case, I would add 1, 1, 1, 1 to 0, 0, 0, 1. And so this goes into the details of how the addition works, but basically you add 1 and 1, which the result is 0, just like when you add 1 to 9, you get 0, and then you add a 1, and then that 1 carries over, and so now you're adding 1 to 1 again, and that carries over, and then you're adding 1 to 1 again, and it carries over, you get 1 to 1 again. So basically it clears it out. So 1, 1, 1, 1 plus 1 equals 0. So you actually don't need to do the 2's complement at the logic level, which is one of the reasons that the 2 complement is used, because you can actually add these values at the binary level, and you'll get the correct value, be it negative or positive. It's a kind of a cool thing. If you're ever interested, again, like I said, bring this up in office hours or in Discord, and I'm happy to sort of just talk about it at more depth. because the circuits are pretty eloquent in the way that they sort of pass these values across, and they kind of daisy chain, and you kind of do it, and then you can make one adder unit that then just sort of works at whatever size, what's called outputting an overflow bit, which the overflow bit then goes into the next stage of the calculation. So to convert a positive to negative number, right? When we convert a positive value in base 10 to negative, we just invert the bits and we add 1. I'm not sure what that statement means, but that's true in binary. So ultimately, to convert 5 to negative 5, we would take the 2's complement, right, which would give us 1. So in the case of 5, we have got 0, 1, 0, 1. If we take the 2's complement, we invert it, we get 1, 0, 1, 0, and then we add 1, and we get 1, 0, 1, 1. And 1, 0, 1, 1 is negative 5. If we look back here, we can see 1, 0, 1, 1 is indeed negative 5. So as I mentioned, if we want to convert it back, we would remove the bit, invert it, so we'd get 1, 0, 0. We would add 1 to that, and then we would multiply it by negative 1. So yeah, this is how we do the 2's complement. So in most programming languages, you can specify unsigned and signed. So in C and C++, you use the keyword unsigned. Also, if you've used the types system, types.h, right? You might be familiar with uint 32 underscore t, or int 30 or int 8 underscore t. In Rust, you actually use u32 or i32. Basically, you do want to sort of designate whether or not a value is unsigned or signed, in particular when it's unsigned. If you're using a value that's unsigned, you really do want to designate that it's unsigned so that you don't accidentally use it in a way that's unintentional, given that final bit. Especially when you're talking about smaller values like char or 8-bit values or 16-bit values, which have a much higher chance of saturating the binary representation of your number. So yeah, if you pass these values around, keep in mind passing an unsigned int into a signed int will change what that value means. So if you cast an unsigned int to a signed int and there happens to be a 1 in the most significant bit, well, guess what? You're going to get a negative number. And so that is important to kind of keep in mind what you're doing. And if you're converting between them, you sometimes want to take the number first, put it into a bigger representation. So say you have a short, an unsigned short that you then want to move into a signed short. Well, first you want to maybe move it into an int first, and then make sure that you're not about to overflow your intended target. So let's talk a little about casting. I already mentioned casting. Casting essentially is taking one number, one value, and sort of turning it into a different value. So in the case of this particular piece of code, we create an integer a, and we have now a representative integer b, an unsigned integer b, and now we take a is going to be equal to the integer version of b. So again, like I mentioned in the last slide, if you say do some logic, and b happens to have a 1 and its most significant location, then now you've taken an unsigned value and turned it into the 2's complement. And given what we know about the 2's complement logic, that's not like multiplying it by -1. It's going to add or subtract some stuff. It's not going to be exactly what you mean. So you do have to kind of take that into consideration. Compilers will implicitly cast a value. So if you create this without doing the cast, it will auto-convert. But some compilers will throw in a warning, tell you that you're losing precision, maybe that you're losing sign information. Some languages will actually give you an error, like Rust will not let you do this. It'll tell you that you're trying to set a value of one type into a value of another. So, friends don't let friends cast implicitly. Pay attention to when you do this, especially if you're writing really high performance code where you do want to do this kind of thing for performance reasons, but don't want to lose the logic. So you do want to kind of make sure that your specifications and the sort of surrounding environment of what you're trying to accomplish allows for this kind of maneuver. Yeah, so like I said before, if you take a value it's an unsigned value, but it has a 1 in the most significant point, and you pass it into, into a signed value, then you're going to get sort of a weird number that you might not intend. So for example, we've got a couple of values here. If you take 0 and you try to logically compare it to 0, you get 1, which makes sense because you're saying is 0 equal to 0, and the answer is yes, which is true. Is -1 less than 0? And yes, it should be -1. It is -1 is less than 0. Is -1 less than an unsigned 0? And the answer is no. And why is that? Because the const 1, -1, is cast to an unsigned value first. And so -1, if you look at it, is all 1s. So if you look at -1 from a cast of an unsigned value, it is greater than 0, not less than 0. In fact, nothing can be less than an unsigned 0. So this will always be false. So in the case of 214 blah 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 greater than this minus 1, is it greater than that? Yes, it's greater than that. And this is actually kind of confusing. Like I mentioned, the negative is always going to be in the absolute value size 1 more than the maximum value of the, and this is actually something that might not be obvious about this number. This is the maximum value of a 32-bit integer, right? This is basically 4 billion divided by 2, or 4 gigabytes divided by 2. So the maximum value of a 32-bit integer is this 2 billion blah 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 of a signed 32-bit number, whereas the maximum negative value of a signed 32-bit integer is -2 billion blah 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 8, whereas that's 7, 8. The reason why is because the 2's complement allows it to be that much more. Okay, this next one's kind of confusing. In the same way that you're comparing two unsigned values, the negative value gets cast into an unsigned value, and in that case, that value is not greater than, because 2 billion, give or take, is half the maximum value of an unsigned 32-bit integer, whereas the maximum negative unsigned, the maximum negative value of an signed 32-bit int, basically converted into an unsigned 32-bit int, is the maximum value, or 4 billion, give it whatever. So in this case, we're actually comparing, is 2 billion greater than 4 billion? And the answer is no. So this one's quite unintuitive, very similar to our -1 is less than 0 unsigned. Similarly, right, we've got this situation of is 2 billion greater than the integer cast of 214 blah 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 8 unsigned, and the answer is actually yes. It is, which is weird. And the reason is I'm actually not sure about this one. This one's a weird one. So this one's really not intuitive. If anybody's really curious about it, please ping me. I'll think about it some more. I'm not aware of this one. And in the last two, if in the sign a -1 is greater than -2, the answer is yes, because -1 is greater than -2. Whereas an unsigned -1 is greater than -2, and the answer is still yes somehow. And this kind of goes back to what I was saying about 2's complement still somehow functioning correctly, but in this case, unsigned -1 is the maximum value of a signed, or of an unsigned equivalent value. Let me go back to this 2 billion greater than the other value. I wonder why. I'll come back to this one, or let me pause and I will try to find the answer. Okay, this one's a tricky one, and it's a good thing that I paused to kind of play with this. So this is actually the programmer calculator I was saying in Windows. So if you'll notice, 2 billion blah 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 is basically literally half the maximum value of a 32-bit integer. You can see here in the binary, it's 0, 1, 1, 1, 1, 1, 1, 1, 1. Okay, so what happens if I remove the last digit with an 8? So that's going to add 1 to all this. You can see now that this value is 1 and 0 for the rest of the number. However, when you cast this to a 2's complement, what do you get? Well, I don't know how to do this manually, but let's do this. No, I don't want to do that. Anyways, the point is, when you convert this into a 2's complement, so if you treat this as a signed number, what you're doing is you're getting effectively negative and 1, 1, 1. So you would take the complement of this, you would convert all of these zeros into ones. Let's do that. Right? These would all be zeros and ones. And then you would add 1. So the value would be 200, blah, 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 plus 1, which would be negative 2,147,483,648. But the negative, now you've converted the whole thing into a signed comparison. And so 2 billion positive is greater than, 2 billion, even though the number, the max is 8. It's going to be greater than that, because any positive number is going to be greater than a negative number. So it's a very curious one. So as you can see, this is a positive number, but oops. Yeah, sorry, I'm not going to repeat this number. It's huge. 7, 4, 8, 3, 6, 4, 7. If I remove the 7 and I replace that with an 8, that's a negative number. So when we cast it to a signed number, we get a negative number, and now we're comparing a positive number with a negative number, and the answer is yes, it is greater. So it's very unintuitive, this one. Cool. I learned something today. So yeah, in C and C++, limits.h defines the maximum values, which is pretty useful. There's also a new, you should also use the new C++, whatever, 11 bullshit. You have the standard numeric limits, and then you can pass to it a particular number and get the maximum and minimum in sort of a portable way. But limits.h is also okay. So C performs sign extension when converting from smaller width to larger width. So this is kind of say I'm taking a signed short, and then I convert it into a signed int. Well, it will extend that value, and it's actually pretty straightforward. The way you would do it is you would just add ones all the way up the stack. As you can kind of see here, y is negative 15213, and the binary representation of that in a short is this. To convert it into a 15213, that is a an integer, like a 4-byte integer, you see these ones, these blocks of ones, which are added to the left side of the number. When you do that with a non-negative number, then you have blocks of zeros. And so this is actually, this is the same thing that happens, by the way, when you logically shift, or you do an arithmetic shift to the right. So say you take a -5, you shift it to the right, then you bring in a 1. If it's 5 and you shift it to the right, then you bring in a 0. So both C and C++, and most languages do this automatically unless otherwise told to do so. Like we mentioned earlier, Java does have, for example, a logical shift operator, so it's specific to doing it in a different way. So again, these are the rules of expansion and truncation. When it's unsigned, zeros are added. When signed, we do the sign extension, and we both get the same, we kind of have the same result. When we're truncating, when we're going from bigger to a bigger number to a smaller number, bits are truncated in both cases, and the result is reinterpreted. So in the case of an unsigned value, you are essentially given a mod operation, and in signed, it's similar to mod, but you can have sort of hijinks with regards to the representations of the values. So just kind of keep that in mind when you're moving up and down. So when we add two unsigned integer numbers, we get 1 bit of carry. We talked a little bit about this when we were exploring the addition of 2's complement numbers to non-2's complement numbers. But what we do is we sort of remove the modulo, the carry bit with this modulo. So what this means is when you're adding two values, and you know, if our resulting value is greater than the maximum value that can be represented by the width, we are essentially subtracting that value, but by we're chopping that piece off. So I actually believe that this this down here, it should be a plus b minus 2 to the power of w. So what that means is, for any number, when you're adding a plus b and the result is going to be greater than 2 to the power of w, then the result is going to be a plus b minus 2 to the power of w. It's just like you're removing. It's a maximum. This is what's called overflow. You're taking two values and it overflows. This is why in the adder circuit in the CPU, when you're building an adder circuit, you have an overflow bit. And this is exactly what happens. If two values are added together and they produce an overflow bit, that overflow bit goes away. So it's as if we just added a plus b and then we had a modulo of 2 to the power of w, right? So you're basically subtracting that value. You're not really subtracting it. It's just the data that you created, that carryover bit, just goes away. It doesn't have anywhere to go, right? So if you're adding two values that overflow 32 bits and they produce a new bit, the 33rd bit, well, the 33rd bit has nowhere to go. And there's no way for the language to tell you that you've overflowed. So some languages will like set off an exception and you can catch it and blah, blah, blah. But like for the most part, this is something you have to be paying attention to. Just don't, make sure that when you're adding two numbers, it's very, you have sufficient what's called overhead. When you do the same thing with signed integer addition, you get 1 bit of carry again, but in this case we're talking about a reduction of 1. So the width is reduced by 1. Your range is reduced by 1. So say like a maximum 32-bit unsigned integer is 4 billion something. So if I added two 4 billion somethings, I would get 8 billion, right? But the result would just be 4 billion something, because it's like 4 billion something plus 4 billion something is equal to 8 billion something minus 4 billion something, and then I get 4 billion, which is weird, but it's what it is. When you do that with an integer, with a signed one, it's 2 billion something plus 2 billion something, you're going to get 2 billion, so because the maximum range is going to be that. So the interpretation is a little bit different, because it's actually a plus b is going to be a plus b mod 2w minus 1 versus 2w. So it's kind of very similar to the same case. If for negative, it's exactly the same, except we're talking about just going to be in the negative. So if you're taking two maximally negative, so negative 2 billion minus negative 2 billion, you're going to get minus negative 2 billion, because you've added them, but then you chop off that carryover bit, and so you can't add another value to the left. This is kind of a slightly lower level explanation of overflow. Again, when you overflow your range, right, and in the case of a signed integer, your range is one shorter. So if you have 32 bits for an unsigned value, your maximum range for an equivalent signed value in 32 bits is only 31 bits. So if you overflow that and the resulting value requires 32 bits when you only have 31, you basically just throw that 32nd bit away, which is like minusing or removing that number. This is the intuition here again is when two numbers add and they overflow your register, your width, your bits, that data has nowhere to go, and as a result just gets deleted. So an example here, so when you take -8 and you subtract -5, you would get -13, right? Which would get you outside. With a carry, right, you have -13. When you remove that bit, you get 3. So that's no good. When you have -8 minus -8, you get -16, and you would get 0. So again, negative overflow. When you have -8 plus 5, you get -3, and the result of that is -3, because you do have a carryover, but it goes away. It's normal. 2 plus 5 is 7. You cut off that extra bit. Again, 7, normal. When you have 5 plus 5, you get to 10. You actually remove that last bit and you get -6. So with signed, it's a little bit different where that overflow bit can behave kind of erratically. Multiplication. So multiplication is actually very similar to addition. But when we multiply, we need to have 2 times W bits of maximal. So say you multiply the value, let's say you have 3, which is 2, like 1, 1, so 0, 0, 1, 1, times 3, which is 0, 0, 1, 1. 3 times 3 is 9, right? So ultimately, you need to have that's going to result in of twice the width of what we just removed. So we have 1, 1, 3, 3 and 3 are effectively 2 width, but in a 4 container. And so we need 4 bits to represent that. And you can actually see, because 9 is 1, 0, 0, 1, 8 plus 1. So now we have twice the width required to represent a multiplication. The example here, say we have 5 times 3. We have 3 bits. The result is going to be 6 bits in width, which when we truncate it, if you want to maintain it to 3, you get 7. And you can see that 4 times 7, 28. When we truncate it back down to 3 bits, we get 4. When we do the same thing with 3 and 3, just like I did with 9, if we truncate it, we only get 1. So we need twice the width. We actually need 6. You can actually see this in the example of 4 times 7. We need effectively 6 bits practically, or twice the width, to represent the full. So 7 times 7, for example, would be 49, and 49 would require the full width of these 6 bits. But if we only have 3 bits to feed it into, then it's not sufficient. Similarly, -3 times 3, which would be -9, we get -1. So you can kind of see the truncation in action here. So multiplication is just like addition, but instead of 1 carryover bit, your carryover can be the width of the number. So you really have to kind of be careful of multiplying big numbers. And this is actually important if you're trying to do like cryptography and like prime number factorization and things like that, where you're multiplying large primes by each other. You very quickly hit this problem. Floating points use a different algorithm, which is something that we'll talk about shortly. So you don't have to worry about it as much. The truncation happens in a different kind of way, but still, it's something that you really do have to pay attention to when you're multiplying integers that are large. So why would you use an unsigned value versus a signed value? Well, for counters, if you are, say, using a an unsigned or a signed number with an array, and you're decrementing your counter, you can very easily get into negative values which can create very unintended consequences, right? Especially in C, where you can basically access any memory in the system. Once you go into, as you know, -1, right? -1 is going to basically be the maximum unsigned value, which is the way that the compiler is going to, read that value, and then you're basically going to some weird location in memory that you don't intend, because then it's the location of A, in this case, plus the maximum value of an integer, which could be who knows where in your system, and potentially outside of the bounds of your physical memory. So, or even the virtual memory that you're provided. So you have to be really careful. This can be quite subtle when you write these kinds of bugs, so it's a lot easier to just use an unsigned value for a lot of these things, or don't decrement counters. But decrementing counters in general is a little bit more temperamental than incrementing them. So yeah, when you want to use a countdown, you're better off essentially using an unsigned value, and this is just a little bit more secure. Even better than using any kind of value is using the size t, which is specifically for the purpose of indexing arrays and things like that, because it's a lot more safe. So yeah, what if count is less than 0 in this case? Well, if count is less than 0 and we're using a size t or an unsigned, the whole thing gets converted to an unsigned, and that 0 is going to be some large integer, and so very quickly we're going to find ourselves running this algorithm for forever. So make sure that you're using proper conventions here. If that maximum if that thing is going to be negative, and you accidentally push this into, this may loop forever, which is not necessarily good. Yep. So you really do want to do this when you're doing multi-precision arithmetic with unsigned. This is, a good way to sort of flatten the context. I'm not entirely sure what usually multi-precision arithmetic, when you're talking about this, is more about using floating point numbers. So I'm not entirely sure. I will follow up on this point in the discussions. So I'm not necessarily sure. Although it does make sense with regards to large numbers. So when you're using unsigned and you're talking about combining different sized integers, there is a lot of truth to that. So you do want to maybe use an unsigned value. And also do this when you're talking about bit masks and sets. As we talked about, never use signed values for bit masks. You're just going to have unintended consequences, and you're also unnecessarily constraining the range of your values and of your set. So your set will never be able to take advantage of the 32nd or the 64th bit in your number. And also the combination of sets and the combination of masks, when you're not being explicit about unsigned and signed, can be really problematic. Cool. I'm going to pause this video here. I'm going to stop it, and then I'm going to reset because this has become quite long already, and I want to give you guys a break as well as myself. So we'll stop it here, and then the lecture will continue with regards to floating point representations.